Lesson number 3, applications to dimension. We want to see how useful dimensions are. What's the concept of dimension? What is it all about? The first use of dimension is to derive equations. We use dimensions to derive equations. Suppose a physical quantity depends on some variables. The method of dimensional analysis can be used to obtain an equation relating the physical quantity to the variables. What does that mean? Suppose you want to calculate the speed of sound in air and you think that you don't know the equation, but you think that it depends on temperature, time, distance, height, it depends on humidity, it depends on all of those things, but you really do not know how to go about it. You can use dimensions to derive an equation to set forth to determine the parameters that can change the speed of sound in air. So we use dimension to determine an equation based on the variables that the physical quantity depends on. Let us see an example. Example number 1. Consider the oscillation of a pendulum. Consider the oscillations of a pendulum. This is a simple pendulum. Consider it oscillating. The period of the pendulum depends on the following quantities. The period of the pendulum depends on the following quantities. The period depends on the mass of the bulb, m, the length of the string, L, and the gravitational intensity. A pendulum oscillating, its period, a simple pendulum in oscillation, its period depends on mass of the bulb, the length of the string, and the gravitational intensity. We can therefore write the equation as period is equal to a unitless constant times the mass times the length times gravity. Now, we do not know whether this tension is directly proportional to the square of the mass, is directly proportional to half of the mass, is directly proportional to the cube root of the mass. We don't know whether the tension is directly proportional to the length or is inversely proportional to the length. And so, for that reason, we introduce powers, indices x, y, and z on these variables, mass, length, and gravitational intensity. We will now use the method of dimensions to determine this x, y, and z. If we see that x is 2, it means that tension is directly proportional to the square of the mass, because if x is 2, then we will have m squared. If x is if y is half, then we will have the tension directly proportional to the length raised to the power half, which means the tension is directly proportional to the square root of the length. That's basically the concept. That is what we have at the back of our mind. Now, there is something I have skipped. We know that tension is directly proportional to a certain quantity. If we say tension is directly proportional to the product of mass, length, and gravity, by the time we are removing the proportionality sign, we introduce a constant. I have just introduced this constant, bearing in mind that you know that, or you have it, that once a proportionality sign is converted to an equal to sign, a constant of proportionality is introduced. And in most cases, it is. Sometimes it's a unitless constant, and sometimes the constant can have a unit, but we can always determine the unit of the constant if we so desire, which is one of the things that we are going to see. I think we're going to solve a question like that, whereby we use this dimensional analysis to see how we can determine the unit of a constant in an equation. Okay, we have said that the period of the pendulum depends on the mass of the pendulum bulb. It depends on the length of the string, the pendulum string. It depends on the gravitational field strength. And we have given a relation between them. Now, let us go step by step. X, Y, and Z are known as powers, and K is a unitless constant. It means it doesn't have a constant. It can be a quantity like half, it can be 5, it can be pi, it can be 20, it can be some other value which does not have a unit. It's a unit, it is a unitless constant. Writing this equation in dimensional format, writing this equation now in dimensional format, it means we have to introduce square brackets. What do we have? We have this tension directly proportional to mass, tension directly proportional to length, tension directly, this is mass, tension directly proportional to length, and tension directly proportional to gravity. Gravity is acceleration. Now you see, acceleration in dimensional format is T raised to the power minus 2. It is displacement on time square. Acceleration is displacement on time square. Please remember that this is advanced level, and so you have to do a lot of research. You have to go back. Looking at what has been done is it's a little bit different from ordinary level. That is why it's called ordinary, and this is called advanced. So you have advanced in discipline, you have advanced in your desires in life, you have advanced in what you want to do. So this equation, as I was explaining, tension is directly proportional to the product of mass, length, and gravity. But we have raised them still to the power x, y, z for gravity. What next do we have? So if the proportionality sign is replaced, for us to replace it with an equal to sign, we introduce a constant. This constant is called the constant of proportionality. This constant is introduced when we are converting a proportionality sign to an equal to sign. So this is mass, this is the mass, the length, and the acceleration, okay. And I want to open out this curly bracket. Remember that this Z is on L and T. So if we open out this bracket, this curly bracket, this K remains, this M raised to the power X remains, this L raised to the power Y remains. Now this L is raised to the power Z. We have L raised to the power Z. And this T is raised to the power minus 2, Z, all raised to the power Z. So we will have T raised to the power minus 2 Z. Remember indices and sets. Remember indices. Yeah, we are actually looking at indices now. So T is raised to the power minus 2, and all of that is still raised to the power Z. So if you open out, it's going to be minus 2 times Z, which is going to give us minus 2Z. Now, we now have the right hand side and the left hand side. This is the right hand side and this is the left hand side. On the left hand side, we have T. On the right hand side, we have K. We have M raised to the power X, L raised to the power Y, L raised to the power Z, T raised to the power minus 2Z. Equating the indices of M, L, T on both sides of the equation, we have to equating the indices of M, L, and T on both sides of the equation we have. For M is only found on the right hand, it is not on the left hand. So on the left hand, the power of M is 0, because M not found on the left hand on this expression implies that it is M raised to the power 0, because anything raised to the power 0 is 1. If T is multiplied by 1, it remains T. And if the 1 is M raised to the power 0, it still remains 1, and it does not change the equation. So it tells us that the power of M on the left hand side is 0, and the power of M on the right hand side is X. So 0 is equal to X. Now for L, we are looking now at all of these dimensions. For L, on the left hand side, there is no L, meaning that it is like t raised to the power, it is like t times L raised to the power 0, because L raised to the power 0 is 1 and t times 1 is still t. Therefore, L on the left-hand side has a power 0. On the right-hand side, L is raised to the power y and L is also raised to the power z. So therefore, the power of L on the right-hand side is y plus z. Remember indices. When the bases are the same, you sum the powers. When the bases are the same, L and L, the power is y and z, so you sum the power. Now, when we look at t, on the left hand side, t has a power of 1, t raised to the power. Once it is just t, it means it's t raised to the power 1, because t raised to the power 1 is still t raised to the power 1. Therefore, the power of t on the left hand side is 1, and the power of t on the right hand side is minus 2z. So we now have three equations to solve. From observation, we already see that x is 0, and we can say that 1 minus 1 is equal to minus 2z. Therefore, z, to have z, we divide both sides by minus 2, telling us that z is equal to half. Let me continue. Telling us that z is equal to half. Now, if we take z, which is a minus half, sorry, because we have now 1 divided by minus 2, which is minus half. If we take z, which is minus half, and substitute it here, we will have 0 is equal to y minus half. 0 is equal to y minus half. Now we carry the minus half across the equal to sign, it becomes half. So y is equal to half. So x is 0, z is minus half, y is half. So what are we going to do with this? We will take this x, y, z and substitute in these equations. We will take x, y, and z and substitute in this equation. When we substitute for x, which is 0, it immediately turns the m, the mass, into 1. Then it will tell us that the tension of the vibrating string does not depend on the mass. I mean, the oscillation, we are not dealing with oscillation. The period of the pendulum does not depend on the mass of the string or the mass of the ball, because we have solved our expression, we have solved this equation, and we have x as 0 and y as half and g as, which is z as minus half. Please, this is where our knowledge of indices is tested once more. We now have to substitute in the original equation, and if we substitute carefully, we have t is equal to k m raised to the power 0, L raised to the power half, and g raised to the power minus 2. M raised to the power 0 is already 1, so it disappears. We are left with k times L raised to the power half multiplied by g raised to the power minus half. Our knowledge of indices tells us that if L raised to the power half times g raised to the power minus half is the same as L raised to the power half divided by g raised to the power half. So since all they are the same power half, we can put them in bracket. We can put them in a bracket and we put a half on. We raise them to the power half. So L divided by g raised to the power half. And we know that when the quantity is raised to the power half, it's like we're looking for the square root of that quantity. So it gives us t being equal to k times root L on g. T equal to root L on g. I wanted to look at it again. Let me take it over again. We have already solved for x, we have solved for y, and we have solved for z. How did we solve for? I went through it, equating terms on the left-hand side to those powers on the left-hand side to powers on the right-hand side. We saw that for m, there was no m on the left-hand side, so the power is 0. On the right-hand side, the power of m is x. On the left-hand side, the power of, there is no L in this equation. This is the equation we are treating. On the left-hand side of this equation, L is 0. L does not exist, so its power is 0. On the right-hand side, there is L raised to the power y and L raised to the power z. So we add y plus z in equal to 0. And on the left-hand side, we have t raised to the power 1. That is why we have 1 equal to t raised to the power minus 2z. Why? Because we are equating indices. That's the rule. Now, if we solve that, we will have x as 0, y as half, and z as minus half. And so we substitute in the original equation m raised to the power x, which is half, l raised to the power y, which is, m raised to the power x, which is 0, l raised to the power y, which is half, g raised to the power z, which is minus 2. So from our knowledge of indices, the equation reduces to t equal to k times root L on G, L on G under square root. Look at it again. This one reduces to z to 1. L raised to the power half, G raised to the power minus half. So it becomes L on G all raised to the power half. Because G is under, it's a denominator. So if it is factored out, it will become G to the power minus half. Beautiful. I hope that is understood. So we see how dimensionally we have been able to determine this equation. We'll be able to derive this equation using dimensions. The equation now is k times the square root of L on G. Or if you're only listening, you might be thinking that is the square root of L divided by G. It is the square root of L divided by the square root of G. The square root of L divided by the square root of G, or L divided by G all under a square root sign multiplied by K gives you the period of oscillation of a simple pendulum. Next example. Consider a stretched string plucked to vibrate between 2 points. As the vibrations are from side to side, a transverse wave is formed. The velocity v of the wave depends on the tension on the stretched string T, the mass of the string M, the length of the string L. The tension on the string T, the mass of the string M, and the length of the string L. If you introduce another factor, or maybe pressure, the pressure on the string, you'll discover that if it does not depend on pressure, when you will solve out, pressure will disappear, just like we saw behind. Now, therefore, the speed is equal to k times t to the power, tension to the power x, mass to the power y, and length to the power z. That's equation 1. So dimensionally, we want to now go again by dimension. Dimensionally, the dimension of speed is L t to the power minus 1. The dimension of tension, tension is a force, is m L t to the power minus 2. The dimension of mass is m, and the dimension of length is L. Again, the dimension of speed is distance on time. Look at this, is L for distance, and on time, time to the power minus 2. And the dimension for force is kilogram meter per second square. Kilogram meter per second square. You see, kilogram is represented by mass, meter is represented by length, and time, second, is represented by time. Kilogram meter per second square. Beautiful. Substituting in equation 1, we have, if we now substitute all of these dimensions in equation 1, we're going to have this curly bracket, because t is 4, so we substitute all of this for t and raise it to the power x, and substitute m and raise it to the power y, substitute for L and raise it to the power z. If we open out these curly brackets, we're going to have m raised to the power x, l raised to the power x, and t raised to the power 2x. This m is raised to the power x, this l is t raised to the power x, t is raised to the power 2x, 2 minus 2 times x, giving us minus 2x. M raised to the power y, this is l raised to the power y. We're still going to do the same. We are equating terms on both sides. Equating the indices of L, T, and M on both sides of the equation we have for L. We see that on the left-hand side, L is raised to the power 1. For L, we have 1 on the left-hand side is equal to, on the right-hand side, L is raised to the power x, and L is raised to the power z. So we have x plus z. For T, on the left-hand side, T is raised to the power minus 1. We are only equating indices. T is raised to the power minus 1. That's it. And on the right-hand side, T is raised to the power minus 2x. So minus 1 is equal to minus 2x. For M, on the left-hand side, there is no M. So M is, the power of M is 0 because there's no M on the left-hand side. I explained that. It's equal to, on the right-hand side, M is raised to the power x, and M is also raised to the power y. So we add the powers. It gives us x plus y. X for this first M, the power of this first M, and y, the power of this second M. So we have now 3 equations. Each time you build these equations, you see that there is one that can easily help you out. We already see that minus 1 is equal to minus 2x, which tells us that x is already half. X is already half. And if we substitute x here as half, we are saying that 0 is equal to half plus y. So what do you think? The half will cross the equal to sign and become minus half. So y will be equal to minus half. So we are going to take y, which is x, which is half, substitute it here, and we solve for z. And if we solve for z, if this is half, x is half, plus z, what will that mean? To get z, we have to take half and cross over. It will become 1 minus half is equal to z. So z is also going to be equal to half. So if we solve that, well, x is going to be half, z half, y minus half. If we substitute for x, y, and z in equation number 1, in the place of x, we're going to put half. So t to the power half, tension to the power half, mass to the power minus half, and length to the power half. What shall we have? We're going to have V equal to K multiplied by TL on M. But mark you, each time we are dealing with vibrating strings, we are looking at the mass per unit length. The mass that we have to work with is the mass per unit length. Mass per unit length. So this mass per unit length is represented here by this L on capital M. This is actually mass per unit length. So this L now, the length now has to go up. I'm sure you are conversant with this arithmetic, with this simplification. So this now L on M is equal to 1 over small m, which when substituted gives us the speed of a vibrating string is equal to a constant times the tension on the mass per unit length under square root sign. Tension on mass per unit length under the square root sign. I want you to take time again and go over it, listen to the explanation, and it's going to be cute. I hope you are enjoying it. I wish you the best. Once more, you are onto Asanji Academy for Global Conquest. The second use of dimension, it is to determine the homogeneity of a physical equation. The homogeneity of a physical equation. What is that big term all about? It's simple. Homogeneity is a physical property which determines whether the units on both sides of the equation are the same. If the units on both sides of the equation are the same, then the equation is homogeneous. The equation is homogeneous. For an equation to be homogeneous, The units on the left-hand side of the equation are equal to the units on the right-hand side of the equation. We know that the area of a rectangle, yeah, a rectangle is length times width. The unit of length, if they are equal to the unit of, if the unit of area, if they are equal to the unit of length times width, then that equation is homogeneous. The area of a triangle is half base times height. If the unit of area is equal to the unit of half base times height, then the equation is homogeneous, as simple as that. We will look at this example. Show that the equation work is equal to the product of charge and voltage is homogeneous. Show that work W is equal to the product of charge and voltage. Show that this equation is homogeneous. As a way of solution, we will look at the left-hand side. The left-hand side, we will work out the units of the left-hand side, which is the unit of work. And work is force times distance. Now, dimensionally, units of force times distance is equal to force is kilogram meter per second square, and distance is meter. So if we simplify this, kilogram stands, meter times meter gives you meter square, and the meter to the power minus 2 remains. So the unit of work is kilogram meter square per second square. This is what we have on the left-hand side. If we also work out the unit of charge times voltage, and it gives us kilogram meter square per second square, then it will mean that this equation is homogeneous. As simple as that. On the right-hand side, this is what we have. On the right-hand side, we will have to work out the units of QV, charge times voltage. We will take them step by step. Unit of charge. Charge, we know that from current times time. Current times time. The unit of current is ampere, and the unit of time is second. From Q equal to IT, the unit of current is ampere, and the unit of time is the second. Now, we have to do a little work on trying to express these volts in its simple form so we can substitute for its base unit. From P equal to VI, we know power is equal to voltage times current. We can make voltage power on current. Now, what do we know? We know that power is work done on time. And we also know that work done is force times distance. So in the place of power, we will be putting force times distance divided by time and divided by current. In the place of power, we are going to substitute work done divided by time. So voltage is power, which is work done on time, divided by current. Voltage is power, which is work done on time. And we know that work done is force times distance. So voltage is force times distance divided by time divided by current. You are in lower C. That should not be a challenge. Okay, it follows that voltage is equal to power, which is force times distance on time. Force times distance is work. Work on time is force times distance is work. Work on time is power, but the power is divided by the current. So this is power. This is work on time divided by current. Voltage is power on time, but power is force times distance on time, the rate of work done on time, divided by the current. So if we simplify that, it shows that we have force times distance divided by current divided by time. We work out now the units of voltage. They become, this is the unit of force. We already determined that the unit of force is kilogram meter per second square. This is kilogram meter per second square times distance, which is in meter, divided by current, which is per ampere, divided by time, which is per second. When we divide, the power becomes negative. Okay, so if we simplify this, the kilogram stands, meter times meter is meter square, second to the power 2 times second to the power 1 becomes second to the power minus 3. And we have ampere to the power minus 1. So we have kilogram meter to the power 2, second to the power minus 3, and ampere to the power minus 1. This is just the unit of voltage. Now we have to multiply it with the unit of charge. What do we get? We now have all of this. Kilogram meter to the power minus 2, second to the power minus 3, and ampere to the power minus 1. This is it. Multiplied by the unit of charge, which is ampere times second. So this ampere to the power 1 multiplied by ampere to the power minus 1 disappears. They check themselves out. Second to the power 1 multiplied by second to the power minus 3 will reduce it. Minus 3 plus 1 will reduce it to minus 2. Meter remains to the power 2 and kilogram remains to the power 1. So the unit of QV is kilogram meter square second to the power minus 2, which is also like so. You see that the unit on the left-hand side is equal to the unit on the right-hand side. What do we conclude? The equation is homogeneous. The equation is homogeneous because the unit on the left-hand side is equal to the unit on the right-hand side. Clap for yourself. Determine whether the equation P is equal to F on A is homogeneous. Pressure is equal to force on area. Force on area. Determine if this equation is homogeneous. We work out the units of pressure. We will get to the answer. We work out the units of force on area. We will look at the answer and we compare. On the left-hand side, what do we have? We have the unit of pressure, which we are going to work them out following this definition. Pressure is equal to rho GH. We know this definition. Pressure is equal to density times gravity times height. Density times gravity times height. If I were you, I'll just pause this lesson and I'll try to work it on a piece of paper and see if I will arrive at the right answer. Unit of density, here we go. Unit of gravity, here we go. Unit of height, here we go. Unit of density is kilogram per meters cube. Unit of gravity, meter per second square. Unit of height is meter. So if we multiply that together, we will have kilogram meter minus 1, second minus 2. On the left-hand side, the unit on the left-hand side is kilogram meter minus 1 and second minus 2. On the right-hand side, what do we have? We will be looking for the unit of F on A. What's the unit of F? Kilogram, F is force, kilogram meter per second square, divided by area, meters cube. So if we take this meters divided by area, which is meter square, if we take the meter square up, it's going to be minus meter square. So minus 2 plus 1 will reduce it to minus 1. The kilogram remains and the second to the power minus 2 remains. What do we see? This unit is the same as this unit. The unit on the right hand side is the same as the unit on the right hand side, which is kilogram meter per second, kilogram per meter per second square. So what do we conclude? The equation is homogeneous. I think we'll look at the last example. Oh yeah, there's a note here. An equation can be homogeneous but not correct. An equation can be homogeneous but not correct. Why? The example of this equation, we know that potential energy is half mv squared. But without this, without half here, if you work out this equation, you'll see that it is homogeneous. But why is the equation not correct? Because in homogeneity, we cannot determine a unitless constant. In working out an equation using dimensional analysis, you cannot determine that constant. We know that this equation is actually half mv square. Half mv square. It's difficult to determine the unit of a constant is unitless, so we can't determine it when we are using dimensional analysis. So conclusively, homogeneity is not the only test, or it's not the true test for the correctness of an equation. You don't just an equation can be homogeneously an equation can be homogeneous, but it is not correct. Why? Because of the absence of a unitless constant. Therefore, the correctness of an equation is determined by one, its homogeneity and the presence or the absence of a unitless constant. An equation can be homogeneous, but it is not correct. Why? Because homogeneity does not take into account the presence or the absence of a unitless constant. When we are working out for the homogeneity of the unit of an equation, we cannot determine the presence or the absence of a constant. Last example, given that the equation P is equal to half KAV cube, where P is power, K is area, V is speed, determine the unit of the constant. Determine the unit of this constant. As way of solution, we rearrange this equation so that we have K standing all by himself. We have 2p on AV cube. If we rearrange this equation, we'll cross multiply. We will have K standing all by himself, and on the left hand side, then on the right hand side, we'll have 2p divided by V divided by the product of V and the product of AV cube. Unit of P is the unit we have said. What were we told? We said P is power. So the unit of P is the unit of force times distance on time. Remember the last example. Work done is force times distance on time. The rate of work done is power, which gives us this unit. The unit of A is meter square. The unit of speed of V meter per second. But remember that in the expression, the speed is raised to the power 3. So we have to cube all of these. If we cube all of these, we're going to have m as m to the power 3 and s as s to the power minus 3. So we will substitute for P, this is P, we substitute for A, this is A, we substitute for V cube, this is V cube, and we simplify. If we substitute, K becomes, we don't need to put a 2 because we are working out unit. 2 does not have a unit. 2 is a digit, it doesn't have a unit, so we keep it aside. We have, this is P and divided by area. That is why we have minus 2 divided by speed. Remember that when it is now divided by speed, this m will now assume a negative sign, minus the power of m will become negative, and the power of s will also assume a negative sign. So that is why we have minus 3, and the minus 3 becomes plus 3. And so this will take care of this. This will take care of this. And this will take care of this. We are left with m cube multiplied by kilogram. Beautiful.